So I've got kind of a fun, different way to do this talk. It's accomplishing a couple goals. So we're going through the fundraising process right now, and all that's been on my mind is these stupid PowerPoint slides. And so I figured I'm going to combine the two because we actually have a pitch right after this. So I'm going to explain this this concept and what Pipeline does in terms of our pitch deck, so you guys get to see that. We started using this tool because it's called Beautiful AI, because one of our potential investors actually, that's one of their portfolio companies. So it's an interesting tool. They claim to actually do AI for your slides, but really all they do is kind of color matching and things like that. So I guess that's considered AI. But so what we're going to talk about today, and if you don't mind, I'm going to update these slides as we're talking here, is this concept of sort of the AI runtime. And actually there's a talk after lunch today by my buddies from Hydrosphere that's going to cover some of these things as well. And this is really bringing life to these machine learning models. Most of the machine learning companies that you talk to or hear about are kind of rooted in Spark, rooted in batch type processes. And this is very boring for us. We've been doing batch, like coming from Netflix, coming from Databricks actually. I used to work there as well. Batch is kind of old school. So we'll be talking about training models off of Kafka streams, continuously training these things, and ways to get these models into production. So let me put this in presentation mode and see if that helps at all here. Get rid of my bookmarks. So we're very much runtime focused, right? So basically, yes, everything that happens, after the initial model training. And I point out the initial model training because we are continuously training these things, and I'll show you guys a bit more on that later during the demo. And also, when you kind of own the runtime, which is one of our goals with PipelineAI, is to own the actual prediction runtime. And if you're familiar, some of you that are 30 and older, I'd say 40 and older, probably remember BEA Systems back in the day, right? Very, very fun company. I used to work there, and we owned the Java transaction space. And so the ability to start to add value into these, sort of transactions, these prediction transactions, is very valuable. You could start to add things like model explanations. You could start to route traffic in smart ways. You can start to combine model predictions into one prediction. Ensembling is what that's called. So there's quite a bit of engineering that comes after the model's been trained. And all the companies up till now really focus on offline hyperparameter tuning is the term. And it's funny, these VCs actually know this term. They know hyperparameter optimization. They don't know hyperparameter tuning. To them, that's totally something different. So you have to, when you speak to these VCs, it's very interesting. And I apologize if there's VCs in the audience, but they kind of lock into certain triplets of words, right? And or tuples of words. And if you don't snap into that, they have no idea what you're talking about. So we do online hyperparameter tuning. So this is as these models are predicting, right? We're collecting data about these things. And we could start to then make recommendations and say, make some changes on the training side. And that will then improve either the prediction performance or the actual system performance of these predictions online. So to contrast this, there's folks like Databricks, H2O, Domino Data Labs. All these folks focus on offline stuff, batch, boring. There's folks like Amazon SageMaker, Azure ML, Google Cloud ML. These are, very much building blocks. They each are, have their cloud lock-in, of course, whereas we're multi-cloud. We write to Kubernetes. This is a very technical audience, so so I'll highlight these things. So just as long as we can get to, basically Docker, and then we can build a Kubernetes cluster, we can deploy Pipeline. So the sort of entry point to Pipeline is the trained model, and you aren't just giving us the actual trained binary or the trained asset, the trained graph and trained weights. You're also giving us what was used to train that model, which hyperparameters were used. So so this is how we actually combine online metrics with offline metrics. We use something called MLflow. Now, this just came out of Databricks a few months ago, and it's essentially an experiment tracking project. So if you go, and very interestingly enough, Databricks chose to not make this an Apache project. And as like a lot of you can imagine, these Apache projects, there's quite a bit of control that you lose when you donate these projects, down to using Nabble for your user lists and stuff. If you try to use anything else, you get your hand slapped. One thing to note too is that TensorFlow itself is not an Apache project. And this lets folks like Google who run this project start to insert things into the open source that are a little bit questionable, right? So they start adding things like, oh, hey, by the way, your model will look really good on a TPU. Here's a free coupon. Go get $300 in credit, from the actual open source tooling and stuff, which is a little bit, crossing the line. But that's one big difference I've noticed going from Databricks into this world of TensorFlow and kind of non-Apache world. But yeah, back to this. So we use MLflow for the experiment tracking, not just offline experiments, but online experiments. So we're constantly feeding MLflow, which is basically just a REST endpoint. We started to build this towards a project called ModelDB. That was popular, a few years ago. That project's kind of gone dormant. It hasn't caught up or stayed current with versions of scikit-learn. There's a lot of rough edges around the TensorFlow support, so versus MLflow, which is very Spark friendly, obviously coming from Databricks, and is very TensorFlow friendly, scikit-learn friendly, and R friendly as well. There's a project called Kubeflow also. We have some opinions on Kubeflow. There's a lot of Google's support going into it, and Amazon is kind of a second or third thought there. So Kubeflow is essentially a Docker registry full of Docker images that all kind of work with each other. And we pull in pieces that we need from Kubeflow, but Kubeflow is a much, much broader thing that you have to buy into. Okay, so yeah, this is one of the things Beautiful AI does, is it recommends ways to lay things out. And then, I don't know if I agree with the layout, but here's a bit on traction. We have a community version. I'm trying not to make this a sales pitch, but at the same time, these pitch decks end up being this. But we do have strong GitHub support. We're just over 30, close to 3,200 stars. And the persona, this is how VC people speak, right? The persona is the app developer, which we're very proud of, because these kind of projects tend to lean towards data scientists or the ML engineer. And we're actually seeing all three of these personas using Pipeline, open source and community, and of course the enterprise version. Let's see. So here's the problem. Said differently, there's all these models being trained. There's tens of these, or hundreds of these training jobs happening here at Twitter, here, everywhere. And then there's this kind of magical handoff. And that's where you hand over your R model or scikit model, and then someone rewrites it in Java, C++, whatever. But the data scientist kind of loses touch with how this model does online. They know how it's doing offline because they've trained, they validated, but they don't really know how this model does online. So there's a lot of metrics just being simply ignored, and this whole disconnect thing. So we're keeping things continuous. The real world is continuous. Fraud's happening all the time. The second that you put these models out, right, these models can get defrauded and start to decay right away. And there's no visibility into this right now. So if you use Pipeline, for example, even the open source stuff, you can push models out side by side and actually send traffic in a shadow mode to different variations of your model. Right now, we find it takes about 1 to 3 months to test any new model variant, or just any new model. We also have been polling people, and we find that less than 5% of all models trained offline end up in production. And it's either because they're typically too slow for applications, because these things are optimized for accuracy and not optimized for prediction throughput and that kind of thing. Right now, most people either spin up a Flask app. In fact, we registered noflaskapp.com, and it goes right to Pipeline. That's pretty much the main like competitor is these bespoke one-off Flask apps that call into a scikit-learn model, or try to call an R model, and like these things take rather upwards of 5 seconds per prediction, and that's not the best way to go. So for full transparency, this world has been like completely busted open by these more modern machine learning frameworks like TensorFlow, MXNet. These things have been designed with online performance in mind. And there's lots of systems level things that happen between the research lab and production, right? So even with like TensorFlow, it's just that TensorFlow actually lets you really do these things where you can fuse together layers, you can change the model from a 32-bit model down to 16-bit and make this like matrix multiplications much, much faster. There's also movement on the hardware side too. There's things like the Google TPU. There's also a company called Cerebras right down the street down in Los Altos, a company out of London called GraphCore that are creating 16-bit native, right, like TPU-like things. These are like deep learning specific chips. And they're like very much targeting TensorFlow. This is how you know TensorFlow is like going to be around for a while. It's not just Google on the software side, it's these hardware manufacturers that are paying very, very close attention. One interesting thing too about these like hardware folks is that they're paying close attention to Kubernetes as well. If you've ever tried to get Docker plus a GPU, like that alone will take up a couple spare weekends. If you try to get Kubernetes plus Docker plus a GPU, that took us all of 2017. And so these guys are trying to make it easier to make these TPUs and these deep learning specific chips work well with Kubernetes, which is very interesting. Okay. Yeah, I can't have a pitch deck without a value prop. So these actually come from some polls that we've been doing. Some of you probably got blasted by us like over the last couple months, begging you to fill out these surveys because we use these to actually show the VCs that people are paying attention to this project. But yes, at a high level, we're like able to actually generate models. So when you have a single model, for example, bottom right, you can't really see it, but you'll have one model that you've trained, and then we can actually generate multiple variations. And these could be GPU-specific variations, TPU-specific, but these are all meant to serve predictions online, right? And there's a bunch of switches you can try that are like unlocking all these systems-level things that I mentioned, right? Like fusing these layers together, dropping down to 16-bit, dropping down to 8-bit. In some cases, people drop down to 1-bit neural network, right? Like, which is very interesting. It shows you that if you have a neuron, a whole bunch of neurons that can only be 0 or 1, it's still relevant the deeper you go, right? Like you could still train something with a very deep neural network at very, very low neuron precision, right? Like numerical precision. The benefit of that, by the way, from a system standpoint is each neuron that participates in these matrix multiplies, the activations and all the fancy stuff happening there, can now stay closer to the ALU, right, to the arithmetic logic unit. So they're not getting, if you have a 32-bit float being multiplied by another 32-bit float, they could potentially end up back in the main memory and be flushed through all the caches. If you have 1 bit by 1 bit, it's like Tetris, right? They could stay super close to the ALU, and then memory movement is very, very fast. And then also I should probably mention across all 3 clouds. So we're actually like pulling each model and spitting out. And so some of our a key part of the metrics that are being generated are cost per prediction. And so because we know the instance type that these like models end up on, these are just Docker containers running within Kubernetes, we can estimate the cost per prediction. If we lose our spot instances throughout the day from Amazon, now the next cheapest cloud might be like Azure, which actually it's almost never Azure because Azure is the most expensive. But we'll start to send traffic over to Google or to Azure. Then once we get those spot instances back, we can then shift traffic back to Amazon. So we can kind of do cross-cloud, multi-cloud cost savings, which we do have people using. All right, this is all go-to-market, blah, blah, blah. Let's see. Let me pull up the demo. So if you go to community.pipeline.ai, you could try this. This actually uses our runtime from the open source. So this is like a nice way to, if you go to quickstart.pipeline.ai, that'll kind of navigate you through the different options here. You can start with the open source and then go bounce into community. We have notebooks and all the usual stuff. We have streams here now too. So you can create a stream, you can send data in, you can hook up and do streaming predictions, right? That's kind of the most obvious continuous like predictions. But you could also wire it up so that you're doing and training these models rather off of these streams as well too. So yes, I have this running in another tab. So there's a bunch of notebooks in here that you could play with. Yeah, how much time? Okay, 5 minutes. So there's a whole ton of samples here. Yeah, anything that's in white, we have the sample right now. All the other ones, we're working on the samples. We support the runtime. We just don't have a coherent sample that matches the rest. We've chosen MNIST, which is the classic handwritten digit, the hello world of deep learning, mainly because it's been implemented in a lot of different languages and ML frameworks. So here's MNIST that's been written, 1, 2, 3, was that 7 different ways. So just straight up Python in Spark. So this is showing JVM runtime, Python runtime, XGBoost, Keras, TensorFlow. So really, like you can, if you think of this at this point as kind of a private Kaggle, right? Like a specific Kaggle specific to your enterprise is just kind of one way to think about it. But it's kind of an extreme sample where there's 7 different implementations of the same model written across all different frameworks. And then here we go and deploy them. I think I was able to get 5 of them deployed before running out of time, just right before this. We've routed traffic to these, so 20% going to each. We could also run them in shadow mode. So I can click this, and that'll put it in shadow mode. It'll still take live traffic, but that traffic won't be returned to the user, right? The other 4 actually return to the user, one of the other 4, but we're still sending traffic to anything that's in shadow mode. And yeah, this comes from like Netflix background and built on some good Netflix like open source. Here, like you can scale it up. We have it limited to 10 containers for Community Edition. You could also set auto scale. If you want to create your own function to define for your auto scale metrics, you can click New, and that'll let you define your own function. This is all serverless. We don't talk about that. That's just implementation stuff. But you can create your own function to do pretty much anything, even the auto routing. So here I could drop this down and say, across all of these model variants or across all these different clouds, right? Like try to minimize cost. And so that's really going to trigger off of that cost per prediction. Or we just want to find the most blazing fast, like the highest throughput version, and make decisions on where you're going to route traffic, 2 minutes. Or you can create your own. So here we can do, oh no, okay, yeah, there we go. So here, this is just kind of a sample input box. This is a JSON representation of an image. I could click predict and see the different, this looks like one of them still starting up. The different implementations back here. And then, yeah, here's a nice little view. So we could see these things lighting up and telling us, throughput numbers and response. Here you can pick any language, grab the snippet of code that will make the call into this service. And then this is something cool. So this is actually showing side by side all, was it 5, 6 versions of this model. And they're all predicting the same value, which is good. These are all the potential values here. This is the same input. This is just some hash. You don't have to worry about actually what that is. It's a hash of the contents of the image so that we can group all the different model variants and what their the physical prediction coming out of each of these variants for the same image. If there was any outliers here, we could go click on it and figure out which variants are giving us. One thing we didn't get a chance to talk about was some of the ensembling, where we could actually combine variants or even go across projects and say, I want MNIST and this is like a little like GitHub star thing that we have when you star the repo. It sends it to a Slack channel. Okay, 30 seconds. So yeah, we could actually ensemble across all these different variations. You can upload a model. You can look at all the metrics in the world. Streams, And what was the other thing I was going to show? Oh, the explainability. So like I said at the very beginning, you can inject value add now to these predictions. So so this actually has two different algorithms for explainability. This is showing the input. This is showing what the actual prediction was and which pixels led to the prediction and which ones didn't. And if you have more algorithms that show up, right, like day 2 after you've deployed this, you would just plop it in, and now you have a third algorithm that's actually sort of intercepting all of these predictions. So that's it. Yeah, hopefully that makes sense.
Great, thanks very much, Chris. There are a few questions.
Can you elaborate a little bit more about the online hyperparameters tuning?
Yeah.
When the models are trained and the more, let's say, outlier data are coming in, how prompt they are to be...
Yeah, I mean, that's a business decision, right? We're the platform that will let you figure out, or that will let you implement the strategy that you want, right? It's a common question with the online training, I think, is what you're getting at, and how sensitive are you to that? Because that could potentially skew the model towards certain trends. So yeah, we actually encourage a discrete continuous kind of thing. So all of our continuous stuff flows through this, and it shows up as a new variant, and it could be shadowed. So we're not actually making changes to the model live. That's something we're very much against, because we saw this cause problems at larger scale, like Netflix. If you're making configuration changes or any kind of change live in production, you don't want that, right? There's always going to be a problem. So the hyperparameter tuning part, we're combining online metrics, which would be relative performance between these models, and we're combining it with the offline metrics as well too, to give a 360. Yeah, that's the key. That way we could say, when you made this change offline, this is what happened online, and this doesn't exist today. Yeah.
I have a quick question about kind of the layers at play here. So I'm trying to derive this from what you've shown.
Yeah.
It looks like you're allowing the user to craft a computation, which then ends up emitting a Docker container as an artifact that's
Correct.
going to be hosted in your system.
Yeah.
What is the interface to that Docker container? How do you implement that?
Yeah.
Each one can host a REST endpoint, or what's the actual
exactly.
interface to the Docker container?
Yeah, and that if you go to the quick start and follow the Docker thing, you'll see exactly what's happening. The short answer is there's kind of a base Docker image. The development version, which is the open source version, has all of the runtimes in there. So it has TensorFlow, it has it's got Python, it has Scikit, it has everything there. So the development version, we extend that base image and burn in the model, and then it's accessible via Kafka stream, so you can make predictions. So so you have to implement the invoke, or the predict method, and that's the contract. That's the only contract between the framework and your model. Just has to have that method called predict.
Or your tools that are outside the container?
Exactly.
What's the contract between that layer, not the base container image?
So yes, everything has to have, there's certain admin endpoints like health checks and things like that that are just REST endpoints. The most basic is a REST endpoint that's listening at /invoke.
So these can host their web server?
Correct, yeah, that's one implementation. There's also gRPC endpoints. There's also Kafka streaming consumer as well. And the developer version has all of them in there, so you can kind of mix and match. The real version, the product version, has separate optimized runtimes for each kind, and then it's just a different way that we do the subclassing of these Docker images. Yeah, good question.
Thanks again, Chris.
Yeah, awesome. Thank you.